welcome you for this third lecture of NPTEL course on earthquake resistant design of foundations. We have in the second lecture we was talking about module 2, which is on shallow foundation, and in module 2 we have covered general requirements in the second lecture. Today we are going to talk about bearing capacity and settlements, that is the second lecture of this module, second chapter of this module, and in this chapter today we are going to talk about bearing capacity and later we will talk about settlement. So, let us see that regarding the bearing capacity for the shallow foundations. When we talk about the bearing capacity, this is given by Tarjagi's theory. You may be aware that Karl Tarjagi was German, and long back he worked lot for the bearing capacity of the soils under certain assumptions. The assumptions made for this theory are listed here, that it is assumed that footing is a long strip or a continuous footing. That means one dimension of the footing is very large compared to another dimensions in the horizontal direction. As a result, one can assume two dimensional plane strain conditions. So, this will be basically two dimensional analysis. The soil fails under general shear failure and the load is vertical and concentrated. The ground surface is horizontal, that means we are not going to consider the sloping ground for the Tarjagi's theory. When we talk about this, then this slide is indicating the failure zones, and you can see that there are zone first, which is elastic zone, which you could see here, and then you do have the plastic zones. So, that elastic zone you could see that this is the here first, then radial shear zone there are two second and here, while third one which is called passive zone, that is also on both sides of the footing. So, these under these three zones the Tarjagi have carried out the analysis for the footing. Here what you could see for this footing, you have the df, which is nothing but depth of the footing, and in the depth of the footing you have this at this point, this what is called, this is called ground level. So, below the ground level up to the base of the footing, which is this line, that is called df, and this is typically a very important dimension for any footing, while width of the footing is at the base, which you could see what is the width of the footing at the base, that is there. Another issues which you could see in this slide are the angle, this angle is alpha, and then you do have this angle 45 degree minus phi by 2, where phi is nothing but angle of internal friction of the soil. So, with all these details we go ahead and continue with the Tarjagi's theory. Most important in Tarjagi's theory is ultimate bearing capacity for a general shear failure or a strip footing, which is given by this relation. You could see this relation, it is most important relationship in to find the bearing capacity of the soils, and this equation is for both C and phi soils. That means it is a mixture of C cohesion as well as angle of internal friction. So, what you do have in this case, that there are three terms. First term is CNC, which is nothing but effect of soil cohesion, and it is assuming the soil is weightless. Second term is you have QNC, QNQ, effect of surcharge, where Q is nothing but called gamma into df, that means unit weight multiplied with the depth of the footing, and then you have the third term which is 0.5 times gamma into B into n gamma, that is represent the weight of the soil in shear zone. In this equation, NC, NQ and N gamma are the dimensionless bearing capacity factors, and they are functions of phi, which is angle of internal friction. So, NC, NQ and N gamma does not have any dimension. C is already coming in this equation, and phi goes under NC, NQ and N gamma. So, that means QU is affected by both C and phi. Beside that, these two material parameters, which is called you may be aware, the shear strength parameters. The QU is also affected by width B as well as depth of the footing. So, you have the higher the depth of the footing or higher the width of the footing, the value of Q is going to increase, though it may not be directly proportional, because there are 3 terms. So, once you increase the value of df, then the value of Q second term is going to increase. If you increase the value of width B, then the last, that is third term, is going to increase. If you increase the value of C, then the first term is going to increase, and if you increase the value of phi, angle of internal friction, then all 3 terms will going to increase, because as you will see that as the value of phi, which is angle of internal friction, increases, the value of NC, NQ and N gamma also increases. Though there is no linear relation, but in general when higher the value of phi, higher the value of these dimensionless parameters. Now, let us see that Tarjagi's bearing capacity factor NC, NQ and N gamma. In this table you can see that there are 5 values that are in the first 4 columns. Phi is listed in the first column, then second, third, fourth NC, NQ and N gammas, then again this is repeated. So, the value of phi in this table is going from 0 to 30 and then 34 to 50. So, you see in this table, as the value of phi increases, all NC, NQ and N gamma increases. However, this increase is not linear. Initially, when you increase the value of phi, the increase in these parameters not so much, but at the higher values there is an exponential change. For example, even when you go 25 to 30, the increase is given in this at the last 2 rows, but when you increase 34 to 35, even 1 degree increase will increase the value NC and NQ and gamma quite much. And further, so the values, for example, NQ started from 1, but end up in 400, same thing is for N gamma. One important point here in this table to be noted, that when the phi equal to 0, the value of NQ is 1 unity and N gamma is 0. This is the position irrespective of the type of theory, Tarjagi's theory, or later on we are going to talk IS code. So, these values are fixed, that is the when phi equal to 0, NQ is 1 and N gamma equal to 0. That means, if I go back in the equation of this the bearing capacity, when phi equal to 0, there is C only, and so this QU term will becomes for C equal to, for phi equal to 0, you can simply write phi equal to 0, Q is C N C plus Q, because and C value is also fixed. For example, for Tarjagi's theory, this equation will be 5.7 C plus Q only, because NQ value is 1 while other parameters are like N gamma equal to 0. So, continue with this. Tarjagi also given the chart to find the value of NC, NQ and N gamma, and this chart is given here, but this chart is for the up to the value of 0 to 40 degree only, and while the table was up to 50 degree. So, this chart can be used. What we can observe, let us do the analysis of these charts. In these charts, what you do have, in this chart you have the, here let me show, you could see that this is NC, NQ and N gamma, that means solid line. Let us talk about only solid line. So, if you see the solid lines, so the value of N when phi equal to 0, this is the case, that means at this axis when the phi equal to 0, your N gamma equal to 0 and as the value of phi increases, n gamma increases, initially small increment because n gamma is this side. So, increase is not much, but as for higher the value it increases drastically. Same is the thing with NC and NQ. Okay. So, that means the increase in the value of these parameters at the initially at the lower value of phi is not so much, but as the phi goes after some certain values there is a tremendous increase. So, that is the case there, and these primes are for the local shear failure. So, which we will discuss these dotted lines later. So, this was about dimensionless bearing capacity factor using Tarjagi's theory. Now, when we Tarjagi also proposed these equations for empirical adjustment for the local shear failure. When you do the have what is general shear failure and local shear failure, we have already discussed in the second lecture, where we have said that in general shear failure are mostly for the dense sand, while local shear failure occurs for the loose sand. Now, when you do have when the for the sand, if you have the value of C equal to 0, that means cohesionless soil, in that case if your angle of internal friction is less than 29 degree, or you do have the relative density less than 20%, in that case we can assume that local shear failure. If you do have the C phi soil instead of the sandy like purely cohesionless soils, in that case that the for C phi soil the strain characteristics will determine local shear failure. So, in that case if your strain is more than 10%, then you can say that it is local shear failure. So, let us say that once it is established that you do have the local shear failure, then the same equation which was given earlier, that means here this is this equation can be used, still the same equation can be used for finding the bearing capacity, but there are two changes in this equation. C is replaced by 2/3 of C. So, that means a factor at 2/3 is coming in the first term, and the dimensionless parameters instead of NC, NQ and N gamma you use NC prime, NQ gamma prime and N gamma prime. These NC and prime that they can also be determined using the same table, provided that instead of phi you get the phi m using this equation, and in this equation that means phi m should be used for this equation, that you can use the value of phi m can be determined, phi m can be determined using tan inverse 2/3 tan phi. So, once you once you know the phi m value, naturally the value of phi m is going to be less than the phi, it is going to be reduced, and once you have the less value and the values of NC and NQ and N gamma are going to reduce. That means naturally you will have NC prime less than NC, NQ prime less than NQ, and finally N gamma also less than N gamma. Okay. So, one way that we reduce the angle of internal friction and then find the value of this bearing capacity factor for the reduced value. Another way, using these curves directly we can read the values of NC prime, NQ, N gamma and N gamma from these charts. But in any case, even if you use these charts, you will see that for the same value of phi, there the values of these factors are get reduced than the original factors. So, this was the case when you have the local shear failure. So far whatever we have discussed was the case for strip footing or continuous footing. However, Tarjagi also have suggested modifications when you use square and circular footing. For square footing, the equation is given here, and what you could see in this equation you see the first term is same, but a factor 1.2 is added on the first term. There is no change in the second term, but while the third term instead of 0.4 have come instead of 0.5. So, that means for square footing there are two changes. The value of the first term, that is cohesive term, have increased, while the last term which is related to unit weight have got decreased. When you do have the circular footing, then again there is in the first term this 1.2 have come instead of C 1.2 C, while in the third term instead of 0.5 you use a factor 0.3, that means it is 60% in the third term has reduced, because instead of 0.5 it is now 0.3. So, 60% reduction in the third term, 20% increase in the first term. So, these are with these two changes these equations can be used for square and circular footing. So far the equation which we have discussed, which was for the QU equation, that is the basic equation, our basic equation is this equation, and in this equation this was for local shear failure. So, that means this equation which we have said, this is the more fundamental equation for the bearing capacity, and that this equation, in this equation it was assumed that water table is very deep, that means you have the depth of water table is quite deep and there is no effect of water table. Now, the question arises naturally, what mean by this water table is very deep? So, that has been clear in this figure. You see in this figure what you do have, you have a footing width B and df is the depth of the footing. Df depth of the footing is from the ground level, this is ground level, this is shown here, and in this case location of water table may be below the base of the footing, base of the footing is here. So, base of the footing, below the base of the footing, if water table is quite deep, and deep means this distance is more than B, that means if from the ground level total distance is df plus B. So, if I put that there will be no effect of let me put it here in the words, no effect of water table, if this dw dash shown in this figure is greater than B, greater than or equal to B. That means if this distance is more than the width of the footing, then there is no correction required to be done. But as the water table rises up towards the ground level, then we need to consider this effect, and how to consider this effect we are going to talk about that. But let us see that, let me explain this. Out of these three terms which you could see in this equation, C n C plus Q n Q, in this equation there is no effect of water table on the first term, and last term will get affected as the water table rises from this position from greater than B to less than B, and the second term will be not affected until the water table reaches up to the base of the footing. But as the water table further rises, it goes above the base of the footing, then both second and third term will be get affected. So, how these two second and third term get affected, that depends on the location of the water table. So, in this slide you could see that again this equation is the basic equation which we have already discussed. Then when the water table is below the base of the footing, for the third term, if dw is greater than B, that means water table is NFD if no correction is required, and gamma need to be taken as gamma T in the third term. However, if water table rises further and it is between the base of the footing and a depth B, that means dw dash is between 0 and B, then the unit weight used in the third term should be calculated using this relation. Now, you can see that in this relation, in any case the gamma is going to be, gamma in no case will be more than gamma T. When you calculate the value of gamma from this equation, it will be always come less than gamma T. Suppose even if I put dw equal to B, then you directly get gamma T, right. So, at the most it can be equal, but it cannot be more than gamma T. If you have dw equal to B, then you have gamma T, but when dw dash equal to 0, that means water table have reached to the base of the footing, then in that case gamma will be simply gamma submerged, and where gamma submerged, you know the gamma submerged is nothing but gamma saturated minus gamma W. So, using this relationship you can calculate the value of gamma submerged. This was the case for the third term. Now, if the water table further rises above, which I show here, above the base of the footing in this slide, then we need to apply the correction in both second and third term. Third term will shut down for this case when the water table goes above the base of the footing, then third term will become gamma into gamma submerged. So, this should be used in the third term. Regarding the second term, it will depend on the location of the water table. If dW shown in this figure is greater than dF, then gamma will be gamma t, but if it lies between between dF and 0, then this is gamma is calculated from this relation, and again here also when you calculate it is going to become less than gamma t. So, in all these second and third term, gamma maximum value may be gamma t and minimum value is gamma. So, gamma in these two terms will be between, it will be greater than gamma submerged and less than gamma t. So, or it may be at the most equal. So, the value of gamma used in this term should lie between gamma submerged and gamma t, where gamma t is nothing but moist unit weight or bulk unit weight. Okay. So, using this moist or bulk. So, this says how to apply the correction for water table in exact sense. Now, beside that, Tarjagi, others researchers also have did the analysis, and so Iscompton's in 1951 did, but Iscompton's analysis was only for when phi equal to 0. This was the case when phi equal to 0, that means cohesive soils only. So, this was the case for cohesive soils, cohesive soils. So, this was the case, and QNU was nothing but QNU is nothing but QU minus gamma dF, which we have already said discussed, or this will be simply QU minus Q. So, QNU will come CU into NC. So, there will be only one term in QU, because Q is it is QU minus Q. So, this can be calculated from this relation here, and now the only one point is left out in this case, that is the value of NC. How to find the value of NC? The Iscomptons have proposed for a strip footing, the value of NC can be found from the first relation, where the maximum value of can be 7.5 irrespective of the value of dF. So, maximum value of NC is 7.5, and minimum you know that if dF equal to 0, then it will be 5. So, NC will be between 5 and 7.5 for strip footing. But if you use square and circular footing, then it is similar exactly. Here correction applied for square and circular footing is same as if you see in the Tarjagi's theory. This factor instead of 5, now this have come to 6, that means 1.2 times of that 5. So, this is the similar correction which has been applied in the Tarjagi's theory for square and circular footing, and the limiting value will be now instead of 7.5 it will be 9. But in case if you have rectangular footing, then you need to apply on the value of NC two corrections. One is due to depth, which is same as earlier, another is B by L, and this first equation need to be used if dF by B is less than 2.5, otherwise this if it is more than 2.5 or equal to 2.5, then it should be used. So, the Iscomptons have given the value of NC for different types of footing, strip footing, square and circular footing, and rectangular footing. Then further some more researchers have worked. Maroff's analysis, Maroff also did the work. Maroff has suggested more corrections on the ultimate bearing capacity. Now, your equation for the bearing capacity is more here complex compared to what we have seen in the Tarjagi. So, NC, NQ, NN, gamma are the factors which was coming earlier also, now also, and they are dimensionless bearing capacity factors, and these factors in the, if you use Maroff's theory, then these factors are given by pendantals, 1921, okay, and n gamma was approximately established by Marov himself. Here in this equation, SC, SQ, S gamma, they are, that means S subscript, S is related to shape factor, while D is related to depth factor and I stand for inclination factors. So, the values of these shape factor, depth factor and inclination factor has been proposed by Marov. So, we are not going to discuss, but the similar things has been done for in Indian standard codes also. Later we are going to discuss that in detail. Then Hansen's in 1957 and 1970 also recommended, and Hansen's recommendation was similar to the Marov with only a difference in the value of n gamma and correction factors. So, n gamma is used indifferently. Then later in 1973 Vesik's bearing capacity factor have come, that is also similar to Hansen, but there was a table, different table to calculate the value of n gamma. So, this was the background before Indian standard code have developed. Now, let us we will discuss IS code recommendation. IS code recommendation have come after Tarjagi, Marov, Hansen and Vesik's bearing capacity factor. So, let us see what is given in IS code, and naturally we follow Indian standard codes to calculate the bearing capacity. So, as for the Indian standard code, the number is 6403 1981 and its title we have already discussed, and the title is I think you may have the copy of the code, otherwise you can have. The title is determination of bearing capacity of shallow foundation. This we have already, title and other things we have discussed in general requirements. Now, in this code, let us first discuss for general C-phi soil, when you have both cohesion and phi component inside the soil, how to find the bearing capacity. So, first equation is for general shear failure, and then what is the modification for this on the local shear failure we are going to discuss. In this slide you could see that for the general shear failure the value of Q mu is given by this relation, and once you have in this case this relation is actually not for Q u, this is for Q n u, sorry about that, it is here it will be Q n u and here also Q n u, because here n q minus 1 has been done. So, this Q n u, that means net ultimate bearing capacity is found this relation, and in this relation what you have, again you have shape factor, depth factor, inclination factor. IS code have suggested that the value of NC, NQ and N gamma are those recommended by Vesik 1973. So, the value of NC, NQ and N gamma given in the IS code are from the Vesik theory, which was the latter theory when the IS code comes in this existence, and beside shape factor, depth factor, inclination factor, which was proposed by Marov, as we have seen in the last slide, Marov have proposed first time, then one more factor have come in IS code, which is the effect of water table. So, effect of water table has been taken in the third term. Now, here is also little difference. When we have discussed Tarjagi's theory, effect of water table was in the second term as well as in the third term. However, in Indian standard code it is only on the third term. So, that we will let us then discuss the first, the effect of water table. So, what you have, that if your water table is quite deep, that means below the ground level at a depth of df plus b, then no correction is required. But if water table rises, then depending on the location of the water table you use the value of W dash. The minimum value of W dash is 0.5 while maximum value is 1. So, this is basically this is going W dash value is between 0.5 to 1. What you do have, that if water table is deep, that means dW dash equal to 0, then the minimum number will be used, that means 0.5. If water table is below the base of the footing and up to a depth of b, then it will be between 0.5 to 1. So, the value of W dash will be minimum value is 0.5, maximum value is 1. Okay. Now, when we do the local shear failure, in that case QNU is calculated from this equation. One thing is missed here. Here it is 2/3 C and C, rest of the things are same, and NC, NQ, and N gamma should be found from phi m, where phi m, as we discussed, like same is in the Tarjagi, that is tan inverse 2/3 of tan phi. So, first calculate the value of phi m, and then NC, after calculating for this value you calculate the NC dash, NQ dash, and N gamma dash. So, this is similar on the same lines as Tarjagi's theory, except that, so general to local shear failure correction is similar as in Tarjagi's theory, except that the water table correction is applied in this case. Beside that, we do have shape factor, depth factor, inclination factor. Shape factor was also proposed by the Tarjagi, because they have given the relation for circular and rectangular footing also, circular and square footing, but other two factors, depth and inclination factors, was proposed by first time by Mehro. Now, continue with this. So, what you have here for bearing capacity factors, this is the table given by IS code, and the values in this table are different than given by the Tarjagi. So, once you use the IS code, then the table for bearing capacity factor should be used from this table, and you can see in this table that the value of phi are going from this phi is going from 0 to 50 degree, and you have NC, NQ, and N gamma, and as before, as the value of phi increases, the NC increases, and the higher values it is exponential increase. NQ is 1 when phi equal to 0 and increases that. One thing is different, at least phi equal to 0, NC was 5.7 for Tarjagi, but IS code recommendation is 5.14, and NQ is 1 and N gamma is 0. So, first row is same like Tarjagi, except the value of NC is different. Then once you know this value of NC and NQ, N gamma, to get the value of NC prime, NQ prime, N gamma prime, just we need to decrease the value of phi, and modified phi is obtained as we discussed already, and then corresponding for that modified value of phi, whatever value of NC, NQ, and N gamma you get from this table will be NC prime, NQ prime, and N gamma prime. Continue with this, because in this equation, when we discuss equation for bearing capacity for IS code, then there are shape factor and depth factor and inclination factor. The shape factor can be found from this table. If you do have the continuous footing or strip footing, then shape factor SC, SQ, S gamma, all three are 1. That means you do not need to have any shape factor basically. But for rectangular, depending on the ratio of B by L, the shape factor is calculated for SC, SQ, and S gamma, and you could see for rectangular footing the shape factor for seat cohesion is more than 1, if, and then you do have for SQ also more than 1, but the value of the third term is decreasing. So, for the rectangular footing, the first two terms get increased, the last term get decreased. The same is the case for square and circular footing, where you have 1.3, 1.2, 0.8 and 1.3, 1.2 and 0.6 is the factor here. Continue with that, you do have the inclination factor, the depth factor first, and then we will talk about inclination factor. The depth factor is a function of angle of internal friction phi, and to calculate for this depth factor, first you need to calculate the value of N phi, where N phi is given by this relation. You could see that here N phi is given by this relation, that is tan square pi by 4, 45 degree plus phi by 2. So, once you know the value of N phi, then depth factor for cohesion can be calculated from this relation. while for other two terms it is 1 if phi is less than 10 degree. That means, this correction need to be applied only when phi is more than 10 degree, and that corrections is given by this relation. Using this relation, the corrections is applied and you can get the value of dq and d gamma, and that can be done. Continue with that. When you do the have inclination factor IC, IQ and I gamma, which is given as per the code, the value of this is given from this relation, where alpha is inclination of the load to the vertical in degrees. That means, suppose if your load is vertical, right, then alpha will be 0, and once your alpha is 0, your IC, IQ and I gamma will be 1. That means, if your load is vertical, no need to apply the corrections, but if your load is inclined, then we need to apply the inclination factor. So, in Tarjagi's theory, it was already an assumption that load is vertical. So, that is why the no corrections was given for inclination factor. Then you do have this this after applying these corrections, and as water table we have already discussed. Now, according to IS code, if you have cohesion-less soils, that means that soils for which you do have cohesion-less soils, that means C equal to 0, you do not have the value of C. In that case, this table can be used to determine which mode of failure, whether general shear failure or local shear failure will be applicable. So, this can be done from 3 factors. Out of the 3 conditions, if you know any of these 3, then you can decide whether it will be general shear failure or local shear failure. For example, if your relative density is greater than 70%, then we consider general shear failure. If it is less than 20%, then local shear failure. Between 20 to 70%, it is interpolation between general and local shear failure. And for interpolation, you need to use both the value of NC, NQ and N gamma. That is very little complex, in the sense that you determine the value of NC, NQ and N gamma first for general shear failure, then for local shear failure, and once you got the values for local and general shear failure, then find the interpolation between these 2 factors to get the intermediate value if it is between 20 to 70%. Let us say if you do not have the value of relative density, but if you know the void ratio, then also you can decide whether it is general shear failure, local. So, if your void ratio is more than 0.55, 55%, sorry, it is less than 55%, then you say the general shear failure. That means it is dense. If it is greater than 0.75%, voids are more, that means it is loose, and then you use the local shear failure. If your void ratio is falling between 0.55 to 0.75, in that case we say that it is interpolation. And using another way, if you know the condition of the soil, if you already declare it is dense soil, go for the local general shear failure. If you say it is loose soil or loose sand, then go for local shear failure. If the condition between loose and dense, that means you do have the medium sand, in that case you need to use the interpolation between local, general and local shear failure. Continue with this. Many times what happens, to determine NC, NQ and N gamma, you require the value of phi, but you do not have in the field the value of phi, particularly for the cohesion-less soils. Again, cohesion-less soils means when the value of C equal to here, that means C equal to 0. This is applicable when this chart will be applicable when C equal to 0, and you do not have the value of phi is not known to you, then you can use, how you can use this chart. You see on this chart the value of SPT n is given here, and for given SPT n value, using this chart you can determine the value of phi from this, and naturally as the value of n increases from 0 to 80, the phi also increases. Of course, for 0 n value there is no value of phi is given. So, the minimum, this chart is starting from 10. When you have the 10, the corresponding phi is 30 degree, but when SPT is gone up to 70, then corresponding n is 40, phi is 44 degree. So, simply this chart is a correlation between SPT n value and corresponding phi value, and in this chart you use the standard penetration rate corrected value of n. So, after applying the correction for overburden pressure, then after using this corrected value, then you can get the value of phi, and naturally you can also classify the type of soil. If you have the value of n very low, less than, let us say very loose on loose sand, but if you have the value of n between this category, that means 10 to 30, then we say medium. If it is less than 10, then it is loose, but then dense. For the dense category more than 30 and less than n value is 50. So, you have medium, dense and very dense, and this chart is applicable for medium, dense and very dense sand, but not applicable for very loose and loose sand, because you do not have this, you need to have this interpolation. It is very like phi value will be very less. So, using this we can find the value of phi. Once you know the value of phi, then you can determine the value of this NC, NQ and N gamma, and calculation can be done. Many times rather than doing the so many calculations and other things like using the chart, the table and the rough idea or the crude idea for relation between n value, phi value and relative density can also be obtained from the table, and this is only for the granular soils. That means again this table is the case when you have this value of C equal to 0. So, here you have, this will be the case C equal to 0. When C equal to 0, when SPT is less than 4, then we say it is very loose sand and relative density is almost 0, phi is between 25 to 30. If it is 4 to 10, then 27 to 32 and then loose. Then if it is medium, that means relative density about 65% and the SPT n is 10 to 30. If SPT is more and values are more than 30 and less than 50, then we say it is dense sand, and the phi values will be between 35 to 40 degree with a relative density of 85%. But if your SPT is more than 50, that means we consider it as a refusal, then the phi will be 38 to 43 degree and relative density is almost 100% with a very dense sand. This was the case when you have a single layer of the soil and homogeneous soil, that means there is no change in the property. But if most of the time in the real scenario, when you go on the ground, below the ground, the properties of the soil are not constant, rather they are varying, C and phi values varies, and normally both C and phi values get increased as you go at higher the depth, because the soils becomes strength get increases. In that case, below rupture, there is a rupture zone within B, as in that case what we do, instead of the using the value of C and phi, we use the average value of C as well average value of phi. Average value of C and average value of phi can be determined from this equation. You have this equation C average and 10 phi average. Using these both equations it can be determined. So, basically this is weighted average C1, and higher the thickness, the weightage is given the thickness of the layer. If this some layer is thick, then that will have naturally more say in that calculation. So, C1 H1 plus C2 H2 plus Cn Hn divided by total depth. The same thing is for this here, but when applying the correction the averaging for phi, it is not with the phi, rather it need to be done with the 10 phi 1 plus 10 phi 2 into then multiply by this. So, this can be average C and average phi should be used in the calculation. Now, summarizing today's that what are the factors which influencing bearing capacity of soils, and let us now bifurcate the equation, basic equation in two parts. One is called cohesionless soils, another is called cohesive soils. So, for cohesionless soils, what you do have this equation, only two terms, because C is 0. So, that means here what you will say that C equal to 0 in this case, and cohesive soils phi equal to 0. There are two terms when C equal to 0, QU QNQ plus 0.5 gamma V N gamma, and these are the factors which is listed, because your NQ and N gamma are function of phi or relative density. So, this phi is coming in NQ and N gamma. then width is also coming and depth will come, because Q is nothing but gamma into df. So, depth will also come in picture. So, that means both depth and width of the footing will influence the bearing capacity for cohesionless soils, for sandy soils. Unit weight gamma is also influencing, and position of the water table, because the water table corrections are need to be applied in these both the terms when water table get rises. So, cohesionless soils ultimate bearing capacity get affected by these factors. But when you see for cohesive soils, which is basically QNU here, which is simply given by one relation C and C, and once you have the C and C, so here it is depends only on the value of NC and C, and NC also in this case, because phi is 0, NC is also constant. For example, for IS code this equation will become 5.14 C according to IS code, and according to Tarjagi's theory this will be 5.C Tarjagi's theory. So, it is very easy to find the bearing capacity in case of cohesive soils, because it is not depending on the width and depth of the footing, it is directly only depending on the value of C. So, C play a great role for bearing capacity of cohesive soils, and higher the C, higher you can expect that. So, with this I conclude today's lecture. Thank you very much.